This is my PDP-1144, and you guys gotta check this out. All right, we're currently booted up into RSX-11M from the Unibone, but here's where things get exciting. If I do a show dev, this is gonna list off all the devices. I'll hit hold screen here because check it out. DM0 is public mounted loaded, label equals Usagi 0, type equals RK07. That is the Fujitsu 2312 hard drive that is in this machine. Now, if I do a dir space DM0 colon brackets 1,54 close brackets and hit return, that is a directory listing of a boatload of files that I just copied over to the real deal Fujitsu 2312. That list of files is coming off of spinning Rust. It's a Christmas miracle, but the amount of effort it took to get here was insane. In case you missed the previous episode, here's a short rundown of what exactly it is that you're looking at. This is a PDP-1144. It's the last non-LSI PDP-11 that was ever built, and I think it's pretty cool because the CPU is spread out across like 8 cards, and this one's pretty tricked out. It's got the commercial instruction set in it. We currently have 1 megabyte of memory in it, but we're gonna push that out to the full 4 megabytes. And I wanna get 16 serial ports plugged into it at some point, as well as network capabilities through a DeLua or a Denua. I have both and I can never remember which one is which, and one of them is definitely better than the other. And we gotta get some kind of storage on it. So for removable storage, we currently have a TU-58 tape drive, and for fixed storage, we've got a Fujitsu 2312, which is an SMD drive that's 84 megabytes, but the PDP-11 can't speak SMD. So we've got an Emulex SC12 controller card in there that's doing a whole lot of translation between what the PDP-11 thinks is an RK611 controller for RK06 or RK07 and the SMD of the Fujitsu 2312. And so that Emulex controller card is going to split up that 84 megabytes from the Fujitsu drive and present it as 2 RK07s and 1 RK06. And the operating system we're installing is RSX-11 because, well, we want to do something a little more tricky with this PDP-11, and that is hook it up to a floating point systems box. So this has changed dramatically since the last time I talked to you guys because we're learning new stuff about floating point systems on pretty much a daily basis. Initially, we were thinking we would have an FPS 100, which gives 8 megaflops of single instruction multiple data performance, and use that as a control processor for an FPS 3000, which should give 18 megaflops of multiple instruction multiple data performance. But we've since learned that the FPS 3000 may not need a control processor, or more correctly, it has a control processor built into it already in the form of a VersaBus controller card that uses an MC68K. So if the FPS 3000 is standalone, then maybe we can't use the FPS 100 with it. And this presents a couple of problems. This is hardware complete, but we don't have any software for it. The FPS 100 we have software for, but it's hardware incomplete. Also, the FPS 3000 looks like it was intended to be interfaced with something that wasn't a PDP-11. Right now, the whole FPS system is a bit of a mess, and we have no idea what the correct path to victory is here. So it's still something that we're trying to figure out in the background. But before we can even get to that, we got to get storage functioning on this thing. So where we left off in the previous episode was that we could actually run the built-in formatting utility on the Emulex SC12. The RSX-11M operating system could see those drives, and we could run the bad block detector utility on them. That seemed to run successfully. It found something like maybe 30 bad blocks out of like 27,000. Clearly, the drive is very healthy, but every time we tried to initialize it, it would say, this is an alignment cartridge, and that's not right. That's not right at all. So this sent us down an insane rabbit hole that consumed my life for a full week. And I think we've got it cracked, but the journey to get there was full of, well, I took 5 pages of notes about everything that we did to figure it out. So I'm gonna run through these 5 pages with you guys right quick, so that way you know exactly what was going on with this and how we got it fixed. And then we're gonna try and get an operating system installed on that drive, and we're gonna try and boot from real deal Rust today. Because this thing gave us so much grief, we tried pretty much every permutation of setting that you could do on the Emulex controller card as well as the Fujitsu drive itself. It always failed exactly the same. Currently, right now, we do have it set up as hard sectored 2312 mode with 2 RK07s and 1 RK06. Now, what we're supposed to do, the first step, is that we run the Emulex formatter. So this is a little formatting utility that is built into the Emulex card itself. And that seems to be finishing with absolutely no error codes. So the formatter on the Emulex card is working just fine. So once we boot up into RSX from the Unibone, then we want to run the bad utility. And what the bad utility is trying to do is it's trying to locate any sectors that are bad sectors, and it creates a little list of those bad sectors so that way the operating system doesn't try to write anything to them. If that's all going well, the next step is to run init. And what this does is it writes the home block to the drive, and this contains the information for the boot block, the bad table, and so on and so forth. But every time we run this, we fail with a disk is alignment cartridge. This is not possible. The Fujitsu 2312 is a sealed drive. There is no alignment cartridge for it. The alignment cartridge is specifically for hard drives that have a removable platter, like the Hawk or like the original RK06 and RK07. The reason that you want to align it is so that you get the heads in the exact perfect position for the removable platter. That way you can swap platters around and everything is always in perfect alignment. And so you didn't want to accidentally format over it and completely destroy this very expensive thing. So looking through the manual, we can see that the last 10 sectors of the last track have a unique format. The first 2 words are for the pack ID, and then the next 2 words are to identify whether it is an alignment pack. And those words have to be all zeros. If there's any bits set in those 2 words that identify it, init thinks it's an alignment pack and it kicks out and quits. So if we look at the dump here, these are all ones, which is not right, but also explains why it thinks it's an alignment pack. And at this point, it makes the most sense to fire up XXDP. XXDP is a diagnostic software suite developed by DEC themselves to troubleshoot a sick machine. And within XXDP is a format utility. But if we run the RSX11 formatter, it fails in a very strange way. And then if we try to run the XXDP formatter, it also fails in a very strange way. If we look at what makes up an actual sector, there's a 16-word preamble, a 2-word header, a 1-word header check, a 4-word header gap, a 16-word data preamble. Then we get to our 256 words of data, which is 512 bytes. Then we have a 2-word ECC, a 1-word postamble, and a 7-word sector tolerance gap. So the format utility has to be able to write down all of the header and footer stuff as well as clear out those 512 bytes of data in the middle. And bad only touches those 512 bytes, but FMT and the XXDP formatter touch the rest. And both of those fail violently bad, which makes sense because both of those were written for an RK611, which is meant to be used with real deal RK06 and RK07s. But we don't have that. We have the Emulex card, which is doing all sorts of really weird translations. So anything that's going to touch the header or footer section of the sector is going to break. It's not compatible with the Emulex. There's a whole section at the end of the manual about modifying the XXDP diagnostics at a binary level to get them to play nice with the Emulex card here. There's a lot of unknowns going on with XXDP and this Emulex controller card, and so I was kind of leery and untrustworthy of it. But also, this should just flat work. Like, Emulex sold the SC12 as a plug-and-play solution for SMD drives on a Unibus PDP-11. Clearly, something is broken, and, well, if we use the dump utility, honestly, it's painfully honest. It should come out as the same 2 words on repeat for the entire sector. But if we look at it, we get a pattern that looks like this. You have the same 2 words on repeat for the first 100 octal words, and then for the next 100 octal words, it's all zeros. And then for the next 100 after that, it's the 2 words on repeat, and then all zeros. And it's a very interesting striped pattern. And honestly, I should have noticed this right off the bat. This is not right, but also, this is uncharted territory for me. I had never done this before. I've never run a formatter and then had to go through and look at the individual bits in the sector to determine whether the format was healthy or not. Once I did catch that this stripe pattern was probably not right, I decided to dig into it a little deeper. And so the bad utility has a couple extra switches that you can use to specify things. Notably, we can specify the 2 words that it uses as the pattern to lay down in every sector. So I came up with this little test routine here that dumps a block of data at memory address 1000, and then we run bad and we use the pattern of all zeros, and then we go back and we dump that same block out. And when looking at it, yeah, the entire sector is completely filled with zeros. And then we run bad again, but this time we're using a pattern of all ones on repeat. And then after bad finishes, we run dump one more time, and now we can see our striped pattern. And we see this stripe pattern on every single sector across the entire drive, which is very weird because bad should be saying that every sector is bad, but bad is bad. There's 2 things that we need to pay attention to here. The first is the pattern in the sector. What's the commonality? What's the common denominator here? And the way that dumps it out isn't very clear, so I had to kind of rewrite it a bit like this. And whenever address bit 6 is set, that's when we have all zeros in that block. But whenever address bit 6 is not set, we get our ones as they're supposed to be. So address bit 6 is the problem here. But why is bad not actually picking up on this? Well, 2 people over on the Discord get all of the credit for this. Balj, B-A-L-J, I think I'm saying that correct, and Suzerain. They were the ones that actually cracked this. Suzerain flexed some impressive Google foo and found a source kit for RSX 3.2. And so Balj then took this bad utility source code and dug into it and started trying to figure out exactly what was going on. The first thing it does is it fills a buffer with the 2-word test pattern repeated. It then writes this buffer to a sector. And if it receives an error during the write, the block is marked bad. It then reads that block back into the same buffer, but it doesn't clear the buffer out. And then it verifies that the buffer is filled with the test pattern that it wrote down. It's reading back into a buffer that's already filled with ones, and so it never actually overwrites the zeros that got written to the drive into the buffer. So the buffer stays all 1. Every sector is indeed bad, but the bad utility is not detecting it because it's not clearing the buffer. Oh, Deck, what are you doing to me, man? Oh, this is crazy. Okay. Well, we need to figure out what's going on with address bit 6, because we can see that every time it's set, we don't actually write any ones down to the drive. So let's pull the Emulex card out and take a look at it. Now this is my spare Emulex SC12 card that let out the magic smoke the first time I plugged it into the Unibus, so something on here has gone horrifically wrong, but we can use this to point at stuff because I don't want to mess with the one that actually works now. And unfortunately for the Emulex card, even though we have a wonderful manual for it, we don't have a schematic for it. But you can see that we have, well, some unmarked ICs over here, or they were probably marked, but they got stickers on them. My guess is that this is probably some kind of AM2901 ALU type thing. And then you have a collection of microcode along the left here that's going to build the entire state machine for controlling the SMD drive, as well as doing all the translation between the Unibus and the SMD. But without schematics, how are we going to know what's gone wrong within here? Well, we do know what the pinout of the Unibus is. This is a well-documented thing, and you can find this in pretty much every PDP-11 manual. So if we look at address line A06 on the correct location on the Unibus, and we follow the trace up, we can see it hits one of these ICs over here that is an AM2908. The AM2908 is a quad bus transceiver specifically designed to work with the PDP-11 bus. However, if we look at this picture that I took, I can see that some of the pads don't look properly soldered. And if we look at the backside, there's a ton of flux from somebody doing some rework here. Let's pull this IC out, put a socket in, and put a new chip in. But pulling the IC was an absolute nightmare. In the process, I lifted a trace, and it took me like 2 hours, but I did finally get a new socket installed and a bodge wire run. And then I stole an AM2908 off of this one over here, which was much easier to remove. It turns out that whatever rework somebody had done earlier really messed things up. And once we had done that little repair, I plugged the card back into the drive. We ran the formatter utility one more time to get a clean, fresh format. Then we ran init, and it initialized perfectly, which then allowed us to create a folder on the actual spinning Rust and copy files down to it. So it's, as far as I can tell, fully functional, and we're ready to start copying files to it, copying a full operating system to it, and hopefully boot from real deal spinning Rust. All that was bad was one transceiver out of the 4 that are on this singular AM2908. What an insane failure. Now, I realize I just summed that up in probably 10 minutes, 15 minutes, I don't know. Filming it took me more than an hour to actually talk all of this through onto the camera, but I'm gonna try and cut it down to something reasonable here. But in real life, that took 4 full days. Like, I'm talking 9 a.m. in the morning to midnight at night for 4 days straight to figure it out. It should not have taken that long, but nobody said I was smart. I'm just too stubborn to know when to quit. All right, let's get to work. Let's try to get a real deal OS onto this thing. If we were doing this like it was 1984, we would still have an insane road ahead of us, but because trying to get a hard drive going on this thing has been like a 6-month goal that I've failed at every step of the way, we're gonna try and use every single tool at our disposal here. So I'm gonna be using a modern laptop so that it's easier to type things in, and we have a full log of everything that happened, and you guys can get a nice little screen capture, and we're gonna use the Unibone to its fullest extent. And Mark is an absolute wizard at RSX, and he was using SimH to build an entire image for me that I can just copy from the Unibone over to the Fujitsu drive without having to go through the nightmare that is sysgenning and then setting up all of the peripherals. We had a long phone conversation about what peripherals I want to get running on this, and so he did all of the hard work of figuring out the sysgen to get all of those peripherals set up, and then figuring out what files need to be copied from a known good RSX 11 install down to the real Rust so that we can pull the Unibone out and boot off of the Rust by the end of the day. All right, so if I do an examine of 10,000, we should have 12700 in there. That should be the bootstrap loader for the DU0 Unibone, so we'll just do an S10000 here, and yeah, there we go. We're loading up. Look at all these devices that are not in configuration. These are things that Mark set up on this particular install of RSX for devices that we're hoping to get installed on this machine in the future. Okay, so let's punch in the date and time here. So 00:00 space 23-AUG-84. We'll see if it takes lowercase. Yeah, it seems to be all right with that. So we'll hit 80 there for how many columns. And then it's gonna install a bunch of things that should make life a lot easier. Like we should be able to do a directory listing now by just typing dir. And now we're fully into RSX, but we're booted off of the Unibone, so we need to run Mark's utility. And I think that utility is in 6,1, so let's do a dir on DU0:6,1. Yeah, there's a bunch of stuff in here. Let's scroll up, see if we find this build. Yeah, there it is, build RSX dm0.cmd. All right, so I think we have to set our directory to that. So we do a set /UIC equals brackets 6,1. And then we do an et bldrsx dm0. My et symbol didn't go through. I wonder if I just didn't hit shift correctly. Let's do an et, there it goes, bldrsx dm0. This should be his utility. I don't know if I have to type .cmd or not. We'll try it without .cmd. We'll go ahead and hit enter. Yeah, there we go. All right, so this is Mark's utility. It says, is dm0 ready? We're gonna go ahead and just hit yes, and it's gonna run off and do its own thing. The first thing it's gonna do is it's allocating dm0, and then it's gonna run bad on it. This is the utility that is bad, but it needs to be run so we know where the bad sectors are. Looks like it already found two, 791 and 1036, another at 2506, 2751. I'm expecting this to find about 30 bad sectors. It's gonna take a little bit of time to run, so we'll just sit here and let it go. Well, it found a total of 30 bad blocks. That is absolutely acceptable, but It appears to have stopped here. I think it's supposed to continue on and run and initialize, do all the deallocation and the mounting and get everything set up and then start the file copy. And the fact that it has stopped dead here is a little frightening. I think I'm gonna have to call Mark and we're gonna have to work this out the hard way. I gave Mark a quick call and we figured out what's going on. Essentially, whenever the bad utility finds some bad sectors, it sets the exit status. So the line in here that said if there's a fault, exit was exiting, but there isn't really a fault. We're expecting it to find some bad sectors. So we had to run the EDT or edit utility to jump in and do some line edits and just edit out that exit status thing. So that way it just skips right over that. And since we've already run bad, we'll go ahead and comment out that line as well. And then we'll just run the whole thing again and it'll skip over bad and start doing the rest. And you can see the rest is just copying files over. So it finished out all the copying, then it did a sys VMR, which is something that we did previously with our sysgen thing. And it's building an entire RSX 11 system on the real deal spinning Rust. But we can't boot it straight from the bootstrap ROM. We have to make that thing bootable by writing the boot block. So we have to boot it from within RSX. This is like super confusing. I'm having a hard time getting the words out. So we're booted into RSX and we want to boot RSX off of the disk. So we have to boot the disk RSX from within the Unibone RSX. This is like, whatever, we'll just type it out. So we'll do an install $BOO. This is the boot command. Oh, it looks like that one's already being used. So then we'll just do a BOO on DM0 colon bracket 1 comma 54 close bracket. So we'll go ahead and hit enter on this and it should reboot RSX, but it's not a full boot, but I do believe that we are in fact running off of the real deal Rust right now. So we can test this by doing a time command here, and I always forget the format of this. Okay, so it's gonna be TIM space 00 colon 00, and then we'll do 23-AUG-84. We'll go ahead and hit enter on that. It does look like it took it, so I don't know. Let's go for broke here. We're gonna do a save space /WB. This should write the boot block and make the Fujitsu 2312 bootable. Boy, howdy, it's doing stuff. Man, I don't know what just happened. This is strange. Okay, 00 colon 00 space 23-AUG-84. Let's do 80 on this. System startup command file. This is doing all sorts of stuff. Okay, maybe we shut it down and try to boot from the Rust without the Unibone in it. I'll just turn the power switch off. We'll pull the Unibone out completely, so there is nothing modern in here anymore at all. We'll put a Grant continuity card in, otherwise the Grant line is going to be broken. And then we're ready to go. Let's flip the power switch back on. Console version 3.40C, halted at 165.714. This is kind of what it always does. This is kind of what I was expecting. But if we do a B space DM, this should try to boot from the Fujitsu drive. Yes! Oh, that's what I'm talking about. Let's go. Oh, we're booting off of the real hardware. This is like 6 months. It is truly a Christmas miracle. That's what I'm talking about. Let's go. All right, the time is 00. The date is 23-AUG-84. The line width is 80. It's... Boot up complete. The Unibone is over there on the desk. It's not in the machine. We just booted off of the hard drive just in time, right before 2026 rolls around. We got it. We're fully booted into the machine. I gotta call Mark and give him the good news, and then I don't know where we go from here, but this is all I really wanted for this year. My Christmas wishes came true. All right, there's one more thing that I want to do because I don't know how to quit while I'm ahead. I want to get this thing up to a full 4 megabytes of memory. I currently have one 1 megabyte card in there, and then these each are 1 megabyte each. So this is the additional 3 megabytes. But what I need to do is I need to go through and set all of the dip switches here correctly so that they all start at the correct memory address and don't overlap. All right, the big dip switch here is for setting the memory address register, and right now with all of them closed, that's going to be starting at a memory address of 0, and that's where the other one is currently sitting, so we want to change this. To get this started at a memory address of 512, we're going to take dip switch number 2 here and just turn it off or open it up. The smaller dip switch here is to set the CSR, so I'm going to set this to this CSR address. Hopefully that's what it needs, and then I just need to go and do this on the remaining 3. After setting the dip switches on the 2 remaining cards, I'll go ahead and slot them into the Unibus here, and this is like the first time power's been into all 4 of those cards at once. There's lots of stuff that could go wrong, so let's flip the switch here. Okay. There's no smoke at the very least. That's good news. All 4 of the cards have green lights on the top. That's also good news. I think we're good to go and boot into the system and see what RSX thinks about it. So at ODT here, I'm just gonna do a B space DM0, hit return, and hopefully I slept it. There we go. It's a full new day, hence the new shirt, and I'm always nervous if it's gonna actually boot, but here we go. It's booting. This is fantastic. There we go, boot up complete. Here's the big one. If I do a show mem, this is gonna tell us how much memory is in the system. Oh, so close. All right, so it says Usagi 1024K. That's a full 2 megs of memory, so that's 1024 kilowords. So we've got half of our memory working, but the other half is not. I really should be editing this video up now, but like it works and I can't not play with it, so editing is going to be a bit tough on this one. But we saw that we had 2 megabytes of memory, which was 2 boards, the boards in slot 1 and 2, but we were missing the other 2 boards that were installed. They weren't being detected. So I pulled board 3 and board 4 out and I swapped their places, and that got us up to 3 megabytes of memory, but that board that was originally in slot 3, this one right here, is not working. But it's not throwing any errors. The red light never comes on. So I think what we've got going on here is we've got some failed dip switches. The little 4-position dip switch for picking the CSR is these 2 rows right here. You can see that on the right side here, all 4 pins are tied together, which makes sense. If I check the continuity across those, yeah, perfect connection. The trace is totally fine. But if I check the connection to the other side here, 4.8 kilo ohms, 4.8, 4.8, I mean, those switches are closed. That should be 0 ohms there. So I think that dip switch has failed. And actually the other one is exactly the same. It's right over here, and you can see that one side of them are all tied together, just like the 4-position one over there. And if I check the continuity on it, yeah, 0.2 ohms, that trace is totally fine. But if I check the continuity to the across the dip switch, these should be closed. And again, we're getting that same 4.8, 4.7 kilo ohms. These again should be 0. So I think what's happened here is that both the dip switches have failed in the exact same way for every position, and they just need to be replaced. Out comes the trusty Radio Shack desoldering iron, and this board was an absolute breeze to desolder. It took less than 10 minutes to get all of the solder removed from both dip switches, and then they very nearly just fell out on their own. And checking the switches on the bench, they're completely hosed. 0 continuity across any of the pins. I'll grab 2 new dip switches and toss them into place and then solder them down with fresh solder. And finally, I'll go through and set them to the correct memory address and control and status register settings. Then I'll just slot it back in place, fire it up, and give it a go. All right, fingers crossed that was it. Let's do a B space DM here. This will start booting us back up into RSX, and not for nothing, I am just over the moon that This boots off of the real deal spinning rust every time I try to do it. This is just absolutely amazing. And the spoiler alert right there, 1,920K mapped. We did it. We did it, y'all. All right, there we go. Show mem. And there it is, Usagi, 1,920 kilowords of memory. One word is 16 bits, so that comes out to a full 4 megabytes of memory. Oh, it's awesome. It's so cool. A couple of dip switches was all that was holding us back from having a full 4 megabytes of memory in this thing. And it's booted off of real deal spinning rust, the Fujitsu 2312 off of an SMD controller. Massive, massive shout out to Mark for just everything, man. This would not have been possible without your help. But also Suzerain, Bowles, Coley, everybody that contributed over on the Discord, like Coley who sent the actual drive to me. Thank you all so much. It's been an insane journey with this thing, and it feels amazing to cap out 2025 with it pretty much completely working. We have an excellent PDP-1144 foundation that we can build upon next year to start working towards some floating point system supercomputing goodness. So I want to thank you all so much for hanging out with me today. I want to wish everybody a Merry Christmas and a Happy New Year's, and I hope your day is absolutely excellent, and I hope to see you in the next one.